Are we alone in the galaxy? Today, we're going to look at what astronomers are doing to answer this question. We're going to look for exoplanets. In this lesson, you will learn how to define an exoplanet. You will learn to analyze the difficulties associated with observing exoplanets. You will describe the current methods for observing exoplanets, and you will determine if a given set of data has evidence for an exoplanet or not. Let's get started. What is an exoplanet? Well, we all know what a planet is. There are 8 of them in our solar system. 1 of them we can always see. 5 of them are occasionally visible in the night sky, and 2 require the use of an optical telescope. An exoplanet is simply any planet that is outside of our stellar system. Astronomers have suspected for a long time that other stars should have planets, just like ours. But there are some technical difficulties associated with observing a planet so close to a star that is so far away. So what makes it so hard to observe exoplanets? Well, 3 main things. First, planets are small. Remember that over 1 million Earths could fit inside the Sun. So while we can see the star at night, the planet that may or may not be around it is really small. Second, stars are bright. You can't see much in the sky when the sun is out. That's why we have to wait for the sun to go down before we can observe anything. It's called light pollution. And third, stars are really far away. We know they're far away, but we're going to calculate just how far away they are for perspective. The nearest star to us, Proxima Centauri, is a little over 4 light years away. A light year is how far light can travel in a year. Light can travel 300,000 kilometers per second. So we need to calculate how many seconds there are in a year. 60 seconds in a minute, 3,600 seconds in an hour, 86,000 seconds in a day, over 31,000 seconds in a year. Times 300,000 gives us 9,400,000,000,000 and change. Over 4 light years for Proxima Centauri means that Proxima Centauri is more than 37 trillion kilometers away, and that's the nearest star. We have observed exoplanets that are nearly 1,000 light years away. Considering these difficulties, we first need to get our telescope out of the atmosphere. There's too much dust, wind, and air molecules. They interfere with our measurements. So we put the telescope in orbit. Then we need to give up on actually seeing the planet directly. Seeing the planet directly would be like trying to see a mosquito fly past the light bulb in your room. If that light bulb were thousands of times brighter, thousands of times farther away, and the mosquito were thousands of times smaller. Not likely. So instead of trying to image the planet, our telescope simply records the amount of light coming from the star. Here's where the magic happens. Remember from chapter 5, we learned that light is a particle, the photon. Our telescope has software that can count every single photon that enters the telescope lens. So instead of producing an image of the star, we get a number. That number remains constant unless something moves between that star and our telescope. The shadow of that object results in fewer photons reaching the telescope. And then we see the number go down. We have observed the shadow of our exoplanet. The brightness of the star is plotted against time, and we get a graph that looks something like this. But be careful. There are other reasons that the amount of light coming from a distant star could go down. It could be an asteroid or a comet in our own solar system. So we also have to make sure that the decrease in light happens periodically, or that it continues occurring in regular intervals as the planet orbits its star. If this doesn't happen, then it is unlikely that we are seeing an exoplanet. I have included a link to some sample graphs from potential exoplanets, and I want you to classify each of them as either a likely exoplanet or not a likely exoplanet.